Hello everyone, I am Dr. Sarika, Assistant Professor of Physics, and I work with Chandigarh Group of Colleges. Welcome back to the lecture series on semiconductors from theory to applications. So this is the second lecture among the already designed 5 lecture series. दोबारा स्टार्ट करना सर कंटिन्यू आप कर दोगे हाँ स्टार्ट Hello everyone, I am Dr. Sangeeta, Assistant Professor of Physics, and I work with Chandigarh Group of Colleges. Welcome back to my lecture series on semiconductors from theory to applications. So this is the second lecture among the already designed 5 lectures. In the previous lecture, we discussed about the drawbacks of quantum free electron theory towards the band theory through the KP model and its conclusion to be able to distinguish between the electronic materials, which are conductors, insulators, and the semiconductors. Now, in this lecture, we are going to study the EK curve and the effective mass. So, from where we start the EK curve is the conclusion of the KP model. So, from the KP model, we got this equation. And we know that from the KP model graphical interpretation, we got alpha A is equal to n pi. So whenever the alpha A is equal to n pi, then we observe the discontinuity in the energy, and we also know this is equal to Ka. Similarly, from this equation, we can say there is a discontinuity in the energy whenever K is equal to plus minus n pi by A. If you look at this expression that E is equal to h bar square K square by 2m, so it is representing a parabola. And what is parabola? It is a continuous curve. So in the continuous curve, we are observing the discontinuity where at K is equal to plus minus n pi by A. So let's see how graphically we can express it. So this is the basic E is equal to h bar square K square by 2m curve. Now, it is a parabola. So whenever the value of K, the x-axis we have K, the value of K is equal to plus minus n pi by A. So for m is equal to 1, that value will be plus pi by A, and on the other side of the axis, it is minus pi by A. So we are observing a discontinuity energy at this point. Alright, and what is the next value? For m is equal to 2, we have plus 2 pi by A and then minus 2 pi by A. That means we will observe the another discontinuity at this point. So how this curve will look like? So this gap on the y-axis when K is equal to minus pi by A, there is a gap between the energy value. While going from 0 towards the x-axis, the value of energy jumped up, skipped up. Let us see the full diagram. So this is the complete picture that we can have E versus K. So you can see there is a discontinuity and another discontinuity is minus 2 pi by A and so on. And what these representing is the different energy level. This is the E1 representing the top of the first allowed band, and then E2 is the bottom of the second allowed band. These are actually representing the energy bands which are allowed, and this gap is representing the forbidden gap. Like this. So these are the three but the forbidden gap. So very first energy level, which is filled, is representing the valence band of the solid, and the very next level after the filled level is representing the conduction band. So in a way, we have the extended form of the EK curve like this. The energy values are extended towards the first zone. We can say it is a from minus pi by a to the plus pi by a. It is representing the first billion zone, and the second minus pi by a to minus 2 pi by a. On the other hand, pi by a to 2 pi by a is representing the second billion zone. So these are the energy values corresponding to the first billion zone. And if you look at this, for example, it is the first field level. So this will represent the conduction band, and this will represent the valence band, and this will represent the conduction band. Okay, so there is a question that we discussed in the previous lecture also. When we come to the conductivity of the solids, for example, we have the iron, we have metals. So in metals, if you look at the free electrons, iron has 8 number of electrons in the valence shell, and on the other hand, copper is having the only 1 electron. But if you look at the conductivity of these metals, copper is actually having higher conductivity in comparison to the iron. Now, the question is why? Iron is having more number of electrons and copper is having less. Then why the conductivity of copper is greater than the iron? So in the next slide, we have the answer. So this is the first EK curve representing the first billion zone, and here we have the point of inflection. These are corresponding to point of inflection where the curve is changing its shape. We look at the effective number of electrons, not the total number of electrons. It is the uneffective. It is directly proportional to the slope of this curve, this dE by dk. And at k equal to 0 and k equal to minus pi by a on this side and plus pi by a on the positive side, the slope of this curve is actually 0. When the energy band is completely filled, when the energy band is completely empty, the N effective is 0. That means there is no conductivity. When it is partially filled, it is half filled up to here, where the point of inflection is, the slope is having the maximum value, and correspondingly N effective is maximum. So what is current or what is conductivity? It is directly proportional to the number of electrons for conductivity that we have. So obviously, copper's this band is partially filled. For iron, it is more than partially filled. So it is giving us the less conductivity in comparison to the copper. So this is the answer to the question we have. Now we look at the EK curve again. This bottom of the conduction band, this is the conduction band, and this is the valence band. So bottom of conduction band and the top of the valence band is actually we represent that EC and EV. And the difference between EC and EV is the band. So on the basis of this band gap, we distinguish properly between the electronic materials. We know in the very first slide of the first lecture we discussed that the bands are overlapped in metals. So there is a little bit gap in the semiconductors, and it's a huge gap of around 5 electron volt and more in the insulators. So this is representing the actually band diagram of the solids. Now, if you look at the x-axis, it is at the same k value. So The solids in which the bottom of conduction band and the top of the valence band lies at same value of K are direct band semiconductors, or usually it happens to the semiconductors or solids, you can say they are also solid. And for the material whose top of the valence band and the bottom of the conduction band is actually lies corresponding to the different value of the K. This representing the indirect band gap materials. Alright. So, what is the problem with this kind of the differentiation between the bands? That when the electron will get excited from the top of the valence band to the very first allowed energy level, that is the bottom of the conduction band, it will leave a hole here, and it is easy for the electron to go to the conduction band, the high energy state, without the conservation of the K. So K is actually conserved here. There is no need to do any extra momentum conservation. But when it comes to the indirect band gap semiconductors, what will happen? It requires an intermediate energy level. So first, the electron will go to the intermediate energy level. Then, so this is at the same K. This is at the same K. And after that, it will go to the bottom of the conduction band. So here it will change the momentum. It will change the K value, and on the going from the top of the valence band to the intermediate level, it was changing its energy. Alright. So this defines the different applications of the material. So this kind of the solid usually are semiconductors like silicon and germanium. They are used in the rectifiers as a p-junction diode and Zener diode. But when it comes to the direct band gap semiconductor, they are usually the human grade, which are gallium arsenide, gallium indium arsenide, phosphide. So these are used for the photoconductivity. For example, when it is get de-excited electron, it will release a energy in the form of photon. Okay, so this defines the applications like semiconductor lasers, LEDs, photodetectors, photodiodes, etc. Now let's come to the another topic, which is the effective mass. We discussed in the first lecture that there is a periodic potential inside the solid, and that periodicity is same as the lattice periodicity. So while moving inside the solid, the electron is actually going through the two kind of region in periodicity. That first, it is in the region 1 where potential is 0, and the second region where potential is have some value like V1. So it is bound in the second region and it is free in the first region. While moving inside the solid, having the periodic potential, it may behave differently from the free electron. So why it is behaving differently? Because its mass is getting changed. So first thing that we need to clarify, that mass cannot be 0, it cannot be negative. But the effective mass is a term which can be 0, positive and negative as well. So how we are going to define this? First, we start from the forces that are acting on the solid. So we have a material, we will apply the electric field, and the force, the external force that we are applying is F is equal to small e, that is the charge of the electron, because we are applying on the electron, and the electric field that we have applied. So small e into the some curly e I have taken to distribution between the energy term. And the F internal. So what is the effect of that external force on the solid. There are actually involving many kind of forces imposed inside the solid. But if we look at the overall, because of the conductivity, it is the electron which is moving inside the solid, and it is moving. Then that means it is covering some distance. Covering some distance, that means it is having some velocity and correspondingly acceleration we have. Hence, the force is equal to, the internal force is equal to m into a. So this m is actually the m star, the effective mass. Now let us have the derivation. We will start from the acceleration of the electron. So electron's acceleration is equal to d by dt of the velocity. Now, what is electron? It is a quantum particle. It is having some wave associated with it, and hence its velocity is the group velocity. Okay. So when we will explain that. So this is the expression for the group velocity. D omega by dk. Omega is the angular frequency, k is the wave number, and then Vg will come in form of the energy. That energy is equal to h bar into omega. So E is equal to h nu. So considering that 2 pi, we have h bar into omega, and if we will derive this d omega by dk, or d is equal to h omega by, so d e is actually equal to h bar d omega. So we will just replace the values that we will have, and 1 by h bar into de by dk is the value of the velocity. Then again we will derive it to have the acceleration. Then we have d by dt the outside and de by dk inside the derivation. So what we are going to do here is we multiply by dk by dt, so that we can take the double derivative separately, that is d2 d2e by dk square, and what we have in the bracket is dk by dt. Now, what is dk by dt? As per the quantum theory, the momentum is equal to h bar into the k, and from here we have dp by dt is equal to h bar into dk by dt, and we will put its value here. And what we are going to have is this rate of change of momentum. So what is rate of change of momentum? It is again the force. Now this is force, this is acceleration. What is this? This is the effective mass. This is the final expression of the effective mass, h bar square divided by the d2e by dk square. So let's look at the graphical representation of the effective mass. So we will compare it for the first William zone from minus pi by a to the positive pi by a. So corresponding to ek curve, we have the velocity of the charge carrier, and then we have the effective mass of the charge carrier, and then we have the f of k, that is the degree of freedom. So when the k value is equal to 0, k value is equal to 0 is representing the bottom of the band. So bottom of the band, the velocity of electron is actually 0. There is no conductivity. That is what we concluded from the previous graph of the ek curve. And when k is equal to plus pi by a, minus pi by a, again the velocity is 0, because it is bound inside the band. The band is completely filled up to the neck. And when it is partially filled, so value of k is actually the point of inflection, where the curve is changing its shape. So the value of velocity is maximum. So it is giving the maximum velocity. The velocity of the electron is maximum, and hence the conductivity is also the maximum. It is moving like a free particle. Now we have the mass. Mass is actually d2e by dk square. That means double derivative this one. And when K is equal to 0, this is having the mass equal to the rest mass of the electron, that is small n, 9.1 with 10 raised to power minus 31 kg. When the value of K is increasing, the effective mass is increasing, and at the point of inflection it has some value which is very high, like infinity. And on the after the point of inflection, again it is having the infinite value, and then further it is decreasing and increasing the K value, that is it is approaching the plus pi by 8, on the other hand minus pi by 8. And then we have the effect. This next graph, we have the degree of freedom, that is f of k. So what is f of k? Is m by m star. Rest mass of the electron divided by the effective mass of the electron, or we can say the charge carrier, because in the semiconductors further we are going to have the hole as a charge carrier. So when m star is equal to m, obviously this will be the value of 1. So the degree of freedom of the electron is 1. And when the m star is less than the rest mass of the electron, it will give us the smaller value. That means the electron is free, its mass is less. Electron is free, its degree of freedom is larger, greater than 1. When m star is greater than m, that means the f of k will be less than 1. So electron is bound and its degree of freedom is less than 1. Okay, so this is what we have for today's lecture, and we'll meet again in the next lecture, where we will discuss about the p-n junction, the charge carriers, which are the electrons and holes, and how the depletion layer is giving us the capacitance in the p-n junction. And further in the upcoming lectures, we will discuss about the applications related to the semiconductor materials. So thank you so much.